So thank you very much for the invitation. It's a pleasure to be in the HCIZ. I've chosen this theme because recently some colleagues asked me about some existing and uniqueness results about what we call Dunkl processes. But I'll do some connections with eigenvalues of matrix valued stochastic processes. Of course, I will give the right definition after. And I wish, presenting a striking connection of this theory with Hurwitz numbers. Of course, it's somehow expected because this theory is closely related to Harishchandra integrals over compact groups. And so Hurwitz numbers will appear naturally. The plan of my talk is the following. I have 4 parts. In the first one, I recall a fundamental work by 2 colleagues, Emmanuel Cepa, who gave up research, Dominique Lepingle, he passed away 2 years ago, but they did really great work on interacting particles. And the problem is that their work remains hidden in some sense. So there are many colleagues who are not aware of their work, their approach, which is quite strong. In the second part, I'll talk about extensions to something called radial Dunkl processes. So there is an algebraic structure behind related to reflection groups. In the third part, I talk about joint work with Dominique Lepingle, which is concerned with reflected Brownian motion in Weyl chambers. So here also there is some algebraic background and even a geometric construction of this process. So I'll give a stochastic differential equation of type Tanaka. Since we are in the Japanese French meeting, I think someone what's called Tanaka. He talked yesterday, but he's not the same. So they see anyway, at the end, of course, I hope talking about this connection to simple Hurwitz numbers. Okay, let me start with Cepa and Lepingle approach. I was glad when Mylène put this equation on her slides. So this is what we call the beta Dyson Brownian motion. Okay, you are not obliged to know stochastic integrals. You can simply think of lambda I as a, let's say, white noise, a Brownian motion plus a Riemann integral involving this singular drift. Okay? At a first glance, what we shall say, okay, we need to start from a configuration where particles do not collide, and then we expect that everything goes right up to the first collision time. There are more information, because when beta equal 1/2, 1, or 2, we have really realizations of these particle systems simply as eigenvalues of matrix-valued Brownian motion. So you take a matrix which is either symmetric, Hermitian, or Hermitian self-dual, quaternionic, and then you put independent Brownian motion. When you compute the eigenvalues, SDE, you will really recover this one. Okay? But for general beta, of course, up to now, in the stationary setting, I mean, when T is fixed, we have this 3-diagonal construction by Edelman. And however, we don't have really stochastic processes realization. What is important for these values is that there is no collisions almost surely between particles. And so you only need to care about the first configuration, and you will get uniqueness and existence and uniqueness result. However, Cepa and Lepingle's theorem are more stronger, and they lie within a more general framework, which is known as multi-valued SDs. The strategy is to, let's say, to do some penalizations. I mean, they add some term, which I will exhibit later, to force your process to exist, and then to show that from geometric considerations, you don't need the term that you already added. The first theorem, so it's quite also impressive because it tells you that for any initial data, even if the particles collide at t equals 0, the beta Dyson differential system admits a unique strong solution which is global in time, so for every time. So whatever you collide or not, your process will exist, is well defined, and it's unique. They also proved another theorem which is kind of 0-1 law for the collision time. So for small values of beta, here let's say beta strictly less than 1/2, you have almost surely that the particle collide, and if beta is greater than 1/2, the particles almost surely do not collide. And this is proved by standard arguments. You need only to construct the right martingales, and then you use what we call Makin argument. In their work also, they considered analogs of these beta Dyson models. Analogs, of course, this is also a folklore, which means that instead of considering, let's say, the function 1/x, the drift, the singular drift, you can also consider something or other functions which behave at the first order like 1/x, okay? So you can either consider the circle version or the hyperbolic also. And they proved the same results. Okay, so let me give the general framework, and even it is a special case of the general framework in order to have let's say easier things. So let's consider a convex closed domain in Rn, and the function which is Laurent semi-continuous convex, which is C1 in the interior of D, and blows up in the complementary of the interior. And then we consider, or we denote n of x, what we call the outward normal vector at x, for x in D minus its interior, so in the boundary. And here comes the name multivalued, because when you, of course, depending on the boundary of your domain of the interior, the outward normal vector is defined by a variational inequality like this. I always miss in which direction, but something like this. So there is an inequality. I don't know exactly which one is inward or outward or whatever, but what is important is that the outward normal vector takes values in a set. And that's why they called these SDEs multivalued, because for every x, it gives you a vector, but you don't know where it is. And this normal vector, of course, will give what are the so-called penalizations in the following sense. So you see, you can consider only this equation, this SDE with Brownian motion, the gradient of this function, which is in the interior, it's regular, so it's the usual gradient. Outside, you can consider what we call the subdifferential, and the subdifferential will give rise to this normal vector. So the whole term given by the gradient and this additional, let's say, boundary process arises from the subdifferential of a convex function. Of course, in the interior, it's C1, so you compute the derivative in the usual way. And otherwise, you will really give rise to this boundary process. And of course, I say the outward in order to add this sign minus to give inwards. So this the inward normal vector will push the process inside in the interior to, of course, to let the process evolve in this state space. And what they prove using this really very impressive machinery is that this SDE has a unique, strong, global, of course, in time solution valued in D. And they recover from their approach two additional important properties is the following one will tell you, and it's expected, that what happens on the boundary has Lebesgue measure 0. I mean, you can neglect it. You can really discard it. So it will tell you that the amount of time here spent at the boundary has 0 expectation. And the other conclusion, or the other byproduct, even it's very important for people doing harmonic analysis, is that the expectation of this gradient, which is singular, is finite. So of course it's singular, but the singularity is of order 1 here. And if you compute this expectation, you will not blow up. Cepa and Lepingle were motivated by reflected processes, of course, in, let's say, smooth or even not very bad domains. And for example, they considered the case of the beta Dyson Brownian motion. So you define your phi by this expression in this domain, what we will call the Weyl chamber of type A. And then outside, you put infinity. So of course, it's really, I mean, this choice will force the process to stay in the domain. And then they proved that the boundary process, as I said, vanishes. So first of all, they put all the terms needed to let the process evolve definitely in the domain. And then they show that the geometry of the state space will, in some sense, make this additional term unuseful. The other choices I already mentioned them here in the blackboard. So you can choose the logarithm of the sine function, and you will recover the cotangent version. And then also this logarithm of hyperbolic sine, and you recover the hyperbolic cotangent. Of course, these particle systems were already considered in the literature. For example, Hobson and Werner considered Brownian motion on the unitary group. You have particles on a cylinder. Here, of course, people also studying Brownian motions on hyperbolic spaces are really familiar with this type of potentials. Okay, now as I said, this state space is known in the realm of reflection group theory as a Weyl chamber of type A. And a natural question which arises is, can we extend Cepa and Lepingle's framework and results to this case? Of course, it's a natural question because other types of Weyl chambers will give you eigenvalues of other matrix-valued processes. I will start with, let's say, some reminders, or maybe I can say crash course on reflection group theory. I need to remind these facts, at least to fix the main objects. So here I'm in the Euclidean setting, and I denote sigma alpha the reflection orthogonal to the vector alpha. And then a root system is simply a collection of finite vectors which is globally invariant by all the reflections. And so, of course, of the vectors with respect of the two reflections corresponding to their vectors. There is an additional condition which has a Lie algebraic flavor because it hints to complex semi-simple Lie algebras. But of course, we can really get rid of this framework and simply say that the system is reduced if and only if the only multiples of a vector inside the root system are plus minus alpha. In the Lie algebra framework, you can find, for example, 1/2, you can find 2 and 1. But here, I only have plus minus, that's it. And this is important also for the existence of Dunkl theory. Then in this root system, since I have this story of positive and negative sides, I can define what we call positive roots, negative roots. So
the idea is very simple. You choose a vector and the roots which are, let's say, on the right, you call them positive, on the left you call them negative, and you can write this more explicitly in this way. So there is you choose a vector which is not in R. R is finite, so you can choose a vector which is not there, and then you define the positive side by this requirement. And of course, your root system will be split into two subsets, what R plus and R minus. So usually we work with R plus. And the example of Cepa and Lepingle corresponds to type A root systems. So you take the canonical basis of Rn, and you take all the vectors plus minus Ei minus Ej. And you can choose this subset and declare it as a positive system. Okay, this is a choice, but there is a whole theory which tells you that all the choices are equivalent. Okay, but I don't need such a theorem. Okay, now it's also standard in algebra, and we would like to work with a basis. A basis is something called simple system, which we will choose inside the positive system. So we have a root system, we choose a positive part, and then a nice result tells you that there is a basis, but with a particular feature that every positive root will be a positive linear combination of this basis. Okay, so this is the additional property. The existence, of course, of a basis is not really quite difficult, but proving that the existence with this property is a bit subtle. And such a subset is called a simple subsystem. Any element of S is called a simple root, and of course the cardinality of the basis is called the rank. Also the name comes from Lie theory. I come back to type A. We take the canonical basis, this root system R. I choose R plus, but once R plus is chosen, the simple system is fixed, is unique. So R plus, if I choose R plus to be this set, the simple system will be this one. So then there are n minus 1 simple roots, so the rank is n minus 1, and this corresponds to the algebra SLN of C for people who are fan of Lie algebras. Okay, I need more data now. So I have R, R plus, and S. With this choice of positivity, I can define a notion of positivity. This is encoded by the Weyl chamber, which is defined as formed by the vectors satisfying this requirement for all simple roots. Of course, the fact that a positive root is a positive linear combination of simple roots gives to you the equality between both. Okay? Another ingredient, we have we defined reflections. So there is a group structure behind, and the reflection group is defined as the group generated by, group generated by all the reflections in R. Of course, all the reflection in R plus. And we have nice simple facts, but also quite important in this theory. The first one is that the reflection group, which for the Lie algebraists is known as the Weyl group, it's finite because it can be seen as the subgroup of permutations of a finite alphabet. So it's a finite group. And most important in the construction of the stochastic processes is the fact that we have a fundamental domain. Simply saying that every point in Rn will have a unique representative in this Weyl chamber. So for example, if you construct a process in Rn, you can do some folding and I mean, construct another one in the Weyl chamber, because every point has a unique representative in the Weyl chamber. And so I can, for example, draw a picture, but it will be there. For example, there is a root system which is quite simple. You take all these vectors. You take all these vectors. And for example, you can choose your positive subsystem such that this is the Weyl chamber. So it's a dihedral wedge of angle pi over 4. Okay? So you see that your space is split into Weyl chambers. Okay? And you have really that the interiors of all these parts are disjoint. And then also you have more that each point here can be mapped to this Weyl chamber. Okay, I give another example which is related to the so-called Wishart or Laguerre processes. So for type A, we already seen that there are reflections which are transpositions. The group generated by them is simply the symmetric group. And the picture I draw here is a special case of what we call type B root systems. So we take, let's say, the A root system and we add these vectors. I can choose R plus to be this set of vectors, EI minus EJ, and the last one, EN. And then with this choice, the Weyl chamber will be given by, let's say, the one of type A and an additional wall at 0. Okay. And here the group, the Weyl group structure is more involved. It's the symmetric group. A semi-direct product with Z2 to the power n means sign changes. I mean, you can permute all the coordinates and flip signs. Okay. I need one more object, and then I'll stop recalling, let's say, facts from group theory. Something called multiplicity function. It's, you know, the Weyl group will act on the roots. It will permute them. And then you will have orbits. You can have one orbit, I mean, if the action is transitive, or you can have two orbits. And the multiplicity function, it's simply a function which is constant on each orbit. Okay? So it takes as many values as the orbit space. And I do a step back. So here, for this type A, there is only one orbit. That's why you have a one parameter beta in the Dyson model. And for the type B, for the Wishart that I will write a few minutes later, we will have two orbits. So we'll have the orbit consisting of EI minus EJ, and the orbit consisting of these vectors. And we can, of course, guess this because, I mean, base it on the length of the vectors. Okay? So here you have square root of 2, and here you have 1. And since we have orthogonal transformations, so we need to keep length preserved. So, so here, for the type A, we have only one orbit. That's why we have one value for the multiplicity function, and this corresponds to this beta. And for type B, we have two orbits, and we will assign two values. So multiplicity function takes two values. And of course, the name multiplicity function comes again from Lie algebraic considerations, because it's a really multiplicity of eigenvalues of operators. Okay. And now the extensions to what we call radial Dunkl processes is as follows. First of all, the extension of this particle systems is the following. What we call the radial Dunkl process. Suppose we have this data, R plus S, the reflection group, Weyl chamber, which is the state space, and the multiplicity function. And I assume that R is reduced. Of course, this comes from harmonic analysis considerations. Where I define the radial Dunkl process as the C-value diffusion. with generator 1/2 Laplacian, so there is a Brownian motion, and then a singular drift, where the singularity comes from this denominator. So you have really hyperplanes like this. So you have your Weyl chamber here. And of course, the singularity comes from the walls forming the Weyl chamber. Of course, since you have a domain with boundary, you need to specify boundary conditions. And here the natural ones, which will correspond to reflected processes, will be that you really impose that your directional derivative in the direction alpha vanishes whenever you touch the hyperplane corresponding to alpha. Okay? So the process, every time it will hit a wall, it will reflect in the direction alpha. So if this wall corresponds to this vector, so if you hit here, you reflect orthogonally with respect to alpha. The second example is now here, what we call the eigenvalues of Wishart or Laguerre processes. And then if you get rid of this dependence on beta, you can call it beta Wishart. I think this is the name people use. You see there is a difference regarding the type A. In the type A, we only had this term. So here for type B, you will see all the walls, means EI minus EJ, EI plus EJ, and here you have EI. So you have a singularity at 0 and here in these two walls. Okay? And the multiplicity function will take two values, beta over 2 and K0. Of course, as in the for Dyson-Brownian motion, for particular values of beta, you have realizations of these particle systems by means of matrix valued processes. In this case, you take a Brownian matrix, which is not necessarily square. You put independent Brownian motion, and you form the radial part. So it will be your process will be B star or B transpose or whatever. And then you look at the eigenvalues of these matrix processes. And of course, the beta equal 1 will be the real symmetric, beta equal 2 will be the complex Hermitian. So this is for algebraic combinatorics related to the Jack parameter. And the K0 will depend on the size of the matrix. As I said, the matrix need not to be square, so it can be rectangular of shape n times capital N, and the multiplicity value will be written in this way. Okay? Of course, for other types of root system also you have similar interpretations with the other Lie algebras. So for example, this one is related to the Lie algebra SON of C, I think, or 2n, I think, SO 2n of C. Anyway, and now the extension of Cepa and Lepingle result is as follows. Provided that all the multiplicity value are positive, which means that you will, your drift will be here to push your process inside the interior of the domain. Okay, because if, for example, imagine K0 equals 0, so you will not see this drift, this singularity. It will be present, but you cannot force your process to leave the wall. So here I assume that all the multiplicity value are positive. Then for any initial value on the closure of the Weyl chamber, so you can start from any initial condition, this stochastic differential equation has a unique, strong global in time solution. And from a probabilistic point of view, if if you are familiar with the so-called local time process, it simply says that your local time near the walls is 0. I mean, it's, you don't really spend time almost surely with respect to Lebesgue measure. And of course, we recover also the other conditions that I put in another slide. Also, we can prove this sort of 0-1 law for the first heating time of the walls. So if we start in the interior of the Weyl chamber, and I suppose that one value, at least, of course, but one value is strictly less than 1/2. Then the radial Dunkl process will heat the wall corresponding to alpha with probability 1. Okay, so this is also this is proved by standard comparison arguments. And what did we gain when proving such results? First of all, we can improve, improve in the sense that we enlarge the set of parameters for which the existence and uniqueness of these eigenvalues or particle systems is valid. With this approach, we can really improve existence and uniqueness results, of course, at the level of eigenvalues. We cannot really improve at the level of matrices. So here we are only dealing with eigenvalues. There is an extension to what we call affine Weyl groups. So this is also for particular values related to matrix valued processes, what we call Jacobi process. Benoit was the precursor of this story with Yann Doumer. Here the story is more complicated because the Weyl group is infinite. Maybe it's less complicated in, let's say, the topological sense, because now we come from the Weyl chamber to the Weyl alcove, which is bounded. So maybe there is more facilities. As I said, for particular values, you have an interpretation by means of unitary Brownian motion and matrix value Jacobi processes. And there is a non-compact case, which was studied by Bruno Shapira, who did his PhD in Orléans, where Cepa and Lepingle were working. So this is expected. And at the level of harmonic analysis of probability, for example, this approach allows to prove a conjecture by Gallardo and Dior on the jumps of not the radial Dunkl processes, which is continuous. So the radial Dunkl processes lives here. But there is an original process which lives in the whole space, which is rather discontinuous. And it's rather discontinuous and jumps along the walls. So it, for example, do that. It arrives here. It can choose the wall here and jumps here. It can evolve, then jumps here, and so on. But then remember that you have a fundamental action. So each point in the Rn has a unique representative here. So this point and this point and this point have the same representative here. And when you do this folding, you get a continuous process. Okay? So there is an original process called Dunkl process. And then with this fundamental action of the reflection group allows to construct what I called radial Dunkl processes, which is rather continuous. Now the approach of Cepa and Lepingle allows to prove a conjecture of Gallardo-Dior, which was suggested by Charles Torossian. I think he needed it for some harmonic analysis stuff. Anyway. Well, now I will move to another direction. So far, I studied this radial Dunkl process, and the Cepa and Lepingle result was extended provided that all the multiplicity values are positive. Now what happens when one multiplicity value vanishes. Of course, as I said, the main point in this approach is that the local time vanishes. And now, so if the multiplicity value vanish, we expect the appearance of local times. However, let's say that when one multiplicity value vanishes, maybe the story is a bit complicated, so let's assume that all the multiplicity values vanishes. It's so okay, maybe it's a matter of for ease of working, but also it's motivated by what we call reflected Brownian motion in Weyl chambers. And the question was, can we write a Tanaka-type formula for this reflected Brownian motion? The study of this process is not new, because Williams studied it for other purposes motivated by cues. So they studied Brownian motions reflected in convex polyhedras. The problem is, of course, for general polyhedra, you don't have, let's say, a natural construction. So people usually define a martingale problem and try to find a solution to prove uniqueness and so on. And of course, as I said, one of the motivations is to find a multidimensional analog of the celebrated Tanaka formula with this local time process. Here, the main point when dealing with reflection groups is that we can have a concrete constructions using rank 1 operators. And this is done as follows. The construction is natural. As I said, you have a process in a Brownian motion in the whole space, and you want to fold it here. So the story is that every time I will project my process on the positive side of a given hyperplane. So I really define this f alpha of x. This is the negative part, and you can see that if x is on the positive part, it's invariant. Otherwise, it is reflected. So f alpha projects on the positive half space alpha x positive. And then, now the complication is, I would like to iterate this f alpha many times. Is there a way to iterate, of course, in finite times, and to get something on the Weyl chamber? And here where group theory comes in, the construction was inspired by work by Bian, Bougerolles-O'Connell on Pitman transformation. The Weyl group is finite, and so it has something called longest element with respect to the generator sigma alpha. This longest element, of course, due to braid relations, it can be written in different ways by means of this sigma alpha. And for any reduced decomposition of W0, I assign an operator, what I call FW0, which is the compositions of all the F alpha for alpha occurring in the reduced decomposition. And now something called Matsumoto lemma. I think it's not Matsumoto also, I think it's quite older from Lie theory. It tells you that due to this braid relation, FW0 is independent of the reduced expression. And then you can see that, of course, every time you project on the positive side, so I think at the end you will end on the Weyl chamber, in the Weyl chamber. So FW0 is independent of the reduced expression and takes value in the Weyl chamber, in the closed Weyl chamber. And now each F alpha is a rank 1 operator. It's a projection. You can apply Tanaka formula, the usual Tanaka formula, many times. And then, of course, we need to analyze the diffusion part and analyze the drift part. And we end up with this SDE. So the reflected Brownian motion constructed in this way satisfies this SDEs. So this is a Brownian motion in Rn. And here we have local times in the direction of the simple root systems. Of course, here the difference with Tanaka formula is that the local time is concerned with the reflected process, not the original one, BT. So it is the reflected one. And here also we can give a condition, or even as necessary as sufficient, such that we can express this local time by means of the one of the original process. So this is also a geometric condition. It says that if alpha is the unique simple root in its orbit, then this term, 1/2, will be the sum over all the positive roots in this orbit of the local time of the original process, not the reflected one. When I put the one-dimensional setting, of course, it's very easy, so we can maybe guess, or we can even imagine that this is the same. But the higher rank case shows that, I mean, the story is quite different. Anyway, we are happy with this process. And for example, I can tell you what happens for this B-type root system. So if the Weyl chamber is here, if I choose alpha, the walls corresponding to alpha are these two ones. And the process can come, near to these two walls, the original wall also. So you will spend, the process will be near all these walls, and we can write the local time process of the reflected process by means of the local time of the original process. And I think this is the only case where this thing happened. I mean, it's really something very particular. Okay, I think I have now 5 minutes. I move to this striking connection with Hurwitz numbers. I talked about Dunkl, so this mathematician is retired, Charles Dunkl. He was in Virginia, and he defined some operators which motivated by algebraic combinatorics. These operators deform the partial derivative. You see, this is a partial derivative, and this is a difference, let's say, operator. When k equals 0, we come back to the two differential operators. And when the root system is reduced, this is the condition I was insisting on. This impressive result of Dunkl tells you that all these operators, which are quite complicated, form a commutative algebra. And this result was very useful for improving, for example, the integrability of quantum Calogero systems, and motivated also other versions, trigonometric, hyperbolic, then Cherednik algebras, and all this stuff. Now the story is that we have the algebra of differential operators and the algebra of Dunkl operators. And Dunkl was seeking an operator which intertwines these two algebras. And of course, which preserves the homogeneous polynomials. He showed that such an operator exists provided that we are in this set. So we, sorry, I forgot the word kernel. He showed that this operator exists if the intersection of all the kernels is trivial, and it's unique. I will end rapidly because with maybe some connection to probability theory. First of all, this operator has a probabilistic flavor because it intertwines the Brownian motion and the Dunkl process. For k equal 1 and the one variable, we recover Pitman theorem, the celebrated Pitman theorem. K equals 0, we can have an integral representation of this Vk. For higher ranks and k equal 1, I said we have a connection to the algebras, and this is at the heart of the work by Bian Bougerolles-O'Connell. We have an integral representation through something called the Distermatt-Heckman measure. And we can also have integral representations for dihedral root systems and A-type root systems. The main question is what happens in general. And in general, with these two colleagues, we found an expression of the action of this VK on homogeneous polynomials. I only gave this formula for sake of information, so not important. More important is this coefficient, which for each element of the reflection group gives this summation. And the summation is over all the factorizations of W into transpositions. And of course now, if K equal 1, this Cm of W will count the number of transpositions, of factorization of W into transpositions. And in the case of the symmetric group, this is called the simple Hurwitz numbers with simple ramifications except at W. And now the open problem is, for example, how to relate or to explain this fact using the connection to Harishchandra integrals, because there is a function called generalized Bessel function, which when k equal 1, it's, for example, and W is equal Sn, it's simply the what we call Harishchandra Zuber, let's say, trace u x u star y du. And for this kind of integral, which is a partition function, if we put here, we compute the logarithm, of course we expect the occurrence of what we call monotone Hurwitz numbers. And we would like to match both worlds. We can discuss later if you want. Thank you very much.
Any questions or comments on Nizar?
Is it meaningful to consider the case of McDonald?
Of course, it's more general, yes. But you will have really some discrete models which will degenerate to this one, of course. And you need also to come from discrete to continuous. For example, in the talk by Imamura, yes, such operators things appear. So this is some sense the lowest level of the energy degenerations. You have Whittaker models, you have Jacobi models, you can, and the highest level is given by McDonald.
Thank you.
Is it interesting to consider Lie groups?
The story started with Dunkl is to get rid of Lie groups, to do harmonic analysis without Lie. But for example, for Whittaker processes, up to now we are stick to Lie groups. And we want to get rid of them because, of course, it's somehow cumbersome.
So if there are no more questions, let's take again the speaker.